Sì, buongiorno signor Frisani, sono Imen Bruis, ero stato in contatto con lei durante questi giorni e siamo contenti di essere con lei. Le presenteremo il nostro Eye Surface Profiler e speriamo che tutte queste informazioni che le daremo potrebbero aiutare. E sì, siamo molto contenti di averla con noi oggi.
Bene, grazie molto del vostro tempo.
Wonderful. And unfortunately, our Italian is so limited that we will speak to you in English, and then Iman
Sì.
will help with translations.
Esatto, se ha bisogno di qualche aiuto io posso aiutarla.
I understand English so well. I'm not fluent in talking, so it's not easy for me to talk, but I can understand everything in English.
Well, your English is very good. Oh, thank you. Okay, that's great. But Iman is here to bridge any gaps should there be any kind of questions or misunderstandings. And Ilse is here as well.
Perfect.
Hi.
Hi.
Io sono Ilse. That's as far as my Italian goes.
Bene.
Welcome.
Thank you. I know some swear words, but I'm not going to repeat those here.
Pizza, maybe.
Pizza, exactly.
Pizza, yes.
Yeah. Mi macchina. Genau. Yeah. Yeah. Very good. Well, thank you so much for making time to spend on this webinar, and we'll do two things. My name is Arnoud Snapvangers. I'm the general manager for Eaglet. And I will take you through a very short introduction of the technology, the background, and etc. And Ilse is our in-house optometrist, and she will discuss a few actual fittings done by our customers. And let's keep it interactive. If you have any special wishes around the presentation, then please let me know or let us know. What are your expectations for today?
Just to learn more about Profiler. And,
Perfect. Okay. No, that's wonderful. So
it's a lot of contact lenses, special contact lenses. So
exactly,
it's very interesting for me to understand better if I can use in my clinic.
Wonderful. Yeah. And you sent Iman a list of the lenses that you work with, and Ilse has found some examples that are very close to exactly the lenses that you work with.
Perfetto. Bene.
Bene. Okay. Andiamo. Up. Oh, well, if that works. Okay. Very good. So the Eye Surface Profiler basically is based on a technology called profilometry.
Yes.
Originally invented by Japanese professor Takeda, and then created into this device at the University of Maastricht in the south of Holland. And that was in the end of last century. And then for a short while, an American contact lens manufacturer actually bought the technology from the university. And they tried to make a device, but they knew, let's call it, they were the specialists on the lens side, so on the application side, but they didn't have enough knowledge to create the actual device. And then the technology went back to the university, and then this is where our team picked it up, and we've developed it to the device that is now. So we currently have about 50 customers worldwide in some 15 countries. And let me tell you a little bit about the technology works. So profilometry allows you to measure not just the full cornea, but also a large part of the sclera. But the sclera doesn't reflect light.
Yes.
And so you need something, and that something is the fluorescein. So you instill fluorescein onto the tear film, and then you flash cobalt blue light onto the tear film, and then the fluorescein molecules will scatter back the light. So you're not dependent on the reflectivity of the surface anymore, but just on the fluorescein being able to scatter back the light. And what we do is from two sides, we project a line pattern, a vertical line pattern, and that then is calculated into a 3D height shape that you see on the right. So that's and I'd say that's the truly rocket science bit of the device. It's transforming these photos into a highly accurate 3D front surface image of the eye.
Okay.
And just to put it in context, of course, keratometry is just a 3 millimeter kind of cornea, central cornea that you measure, and then you have the large cone Placido devices that measure between around 8 millimeters, and then the Medmont does a little bit further, goes out to 10. Pentacam goes a little bit further, about 11, and but the eye surface profiler allows you to really measure the full front surface of the eye. So whenever you fit a lens, there is no need for extrapolation anymore. That's the essence of it. And another thing is that our technology measures height and not curvature. And in the end, if you want to fit a lens, then you should always do so from a height kind of point of view, and not from curvature.
Okay.
And just to give a quick idea on the diversity of eyes and why it is really worthwhile to measure the wider diameter that the eye surface profiler enables, is this research done by Jerry Legerton, so an optometrist in the US. He had about 300 eyes measured, and what you see on the horizontal line is basically the diameter, and vertically it's the sagittal height. And you see, the further out you go, the more variation there is between the flattest and the steepest, deepest eye. And so, just to illustrate, we've drawn this chord line of 14 millimeters, and you can see at 14 millimeters for this population, between the flattest and the steepest, or the highest and the lowest sagittal height, there was a difference of 3 millimeters. And this is, of course, only over 1 meridian, and then we haven't even touched about the asymmetry of the eye.
Okay.
So just to recap, 20 millimeters we measure both in horizontal as well as in vertical. It's about 500,000 data points. We measure height, and this is the basis for fitting all types of lenses. So starting with ortho-K up to RGP, soft, hybrid, and Scleral. And currently we have 35 lenses integrated, and Ilse will go really in depth into that from about 18 different lens manufacturers, and we constantly are on the lookout to expand and to invite other labs on board as well, because we deliberately have chosen ourselves not to produce lenses so that we could be an open platform and open the door to any lens manufacturer that wants to collaborate with this.
Okay.
Accuracy, there's a number of, I think we're about 17 different peer-reviewed articles right now out there. And the first one was by Rob Iskander, about the accuracy of the device, and he was able to show that for the cornea we have a 2 micron accuracy, and for the sclera we have a 10 micron accuracy. And what you see on the screen here are 2 height measurements of a test surface, and you see on the right there's the difference map. And it is, except for the very, very edge of this map, it is all within 1 micron difference.
Great.
And So yeah, that's what we're trying to do. We collaborate with the specialty lens manufacturers. We've got we support a lot of research on that as well, of course. And one of these research projects showed that this was a retrospective study done by one of our customers in the UK, Brian Tompkins, and he measured 49 eyes. Oh, sorry. Let me take one step back. He had 49 eyes that were fitted with a Scleral lens, but fitted in the old-fashioned way with the fitting set. And for those 49 eyes, he had a variation between 2 refits and 7 refits, and his average was just above 3 for that population. And so he then next invited all of these patients back into his practice.
Yes.
And he measured them with the ESP. We ran the algorithm that we have, and in 85% of the time, our algorithm pointed at the final best fitting lens that he had achieved doing the old method.
Okay.
And so with him, we're now working to reduce the average of 3 that he had, or a little bit above 3, to 1 point something. And so improve the patient experience, reduce the cost, reduce the chair time, and overall get better fitting lenses. And that's the essence of our device.
Great.
So this is the theory, and but practice is more interesting, of course. So Ilse, when you're ready, let's switch over to you.
Oh, ready.
Yes. All right, you should be able to see the software right now. Is that correct?
Yes, we do.
All right, so the task is up to me to do the fun part, because of course the theory behind the device, we have to tell you this, but the most fun part is after we've been taking a measurement, what do we do with it? So that's up for me to explain to you. If I'm going too fast at any times or you don't understand something, feel free to interrupt me. That's no problem at all. I'm here to answer your questions.
Okay.
So this is an image you'd normally see after taking a measurement. So you see a full map over here. This is a very good map. If you look up here, you can see it's a scale of 20 millimeters. So this map has a width of 20 millimeters. Yeah. And to start by the beginning, the interpretation is a little bit different if we're used to regular topography. In this map, everything that's more red means it's more elevated, so it's higher. Everything that's blue means it's lower. So we do not talk about curvature or steep or flat, we talk about high and low.
Okay.
We can calculate the curvature, but we directly measure sagittal height. So we give curvature data, however, everything how we measure is in sagittal height. Mm-hmm. And the way we get this information, we calculate 2 spheres. One sphere is from the cornea, which is this green dotted line you can see over here. Mm-hmm. I'll enlarge it a little bit. And the other line is an orange dotted line, that's the sclera. So we create a map of the cornea and we create a map of the sclera. Because they're not on the same level, we kind of have to paste these 2 images together. And we do that on these points over here, where they intersect. That's also the red ring you'll see on the map over here. Mm-hmm. So the red ring in this area is not an elevated area. It's just a mathematical equation, a calculation we have to make to paste those images together. So that's not an artifact. It's always supposed to be there. You're gonna have this in every measurement. So what we then have is one bisphere, one average bisphere, and everything that's above this is higher, is red, and everything that's lying below that sphere, it's blue, so it's lower.
Clear.
Is that clear so far?
Yes.
All right. So in the example over here, we have a keratoconus patient. You can see that because he has a very red elevation over here in the center.
Mm-hmm.
If I move my mouse over here, this cone is 250 microns elevated. So the next time you take a measurement, you can see, is it higher than 250? Is it lower? And you can see if there's any progression.
Mm-hmm.
So for this patient, we probably want to fit a scleral lens on there. What kind of scleral lenses do you mostly work with? What manufacturer?
Oh, several manufacturers, and in Italy we have two good labs. And but I tried Zen lens, I tried ICD, I tried what can you know in Procornia. I used it in the past. I know several manufacturers.
All right. We do have the fitting sets of Soleco Incorporated. Unfortunately, I do not have them opened up right now.
I know them. I know them.
All right, awesome. ICD, we're working on it. The algorithm I do have ready is ZenLens, and that's what I can show you.
Yeah.
So if we have this keratoconus patient right here, we probably want to fit a scleral lens on it.
Okay.
So we can check the HVID, which is 12.6. It's quite large, so we probably want to fit a 17 millimeter Zen lens for this patient.
Mm-hmm.
So I'm gonna go over to our first fit lens algorithm, which is up here.
Mm-hmm.
I'm gonna give it some time to load up. There you go. And I can select a supplier. So for Zen lens, we need to go to Bausch & Lomb, and we're going for a 16.
Yes.
All right, I'll click on this button, and this button is going to calculate what lens to put on there. So this is an online software system. That means if there's any changes in the algorithm, I can change them at home, and everybody will have the update immediately. So over here, it's finishing calculating. It's telling us to have a central volt of 4,950.
Mm-hmm.
This BCR, and a little bit of toricity.
Okay.
All right, now we can check this, of course, because what the algorithm does is awesome, but we want to make sure it's correct.
Yes.
So the way we can do that, over here you see this little section, sagittal height.
Mm-hmm.
From here on, we can calculate the sagittal height at any given chord length. So in this case, we're working with a 17 diameter Zen lens. So I want to know the sagittal height of this eye at 17 millimeters.
Okay.
So I type in 17, I'm going to start calculating, and I can see that the average sagittal height is 4,810. So what it does, it's adding about 200 microns, 150 microns to get a little bit of tear layer,
Mm-hmm.
and for the settling of the eye. So this number is always going to be a little bit higher than the actual sagittal height. And
Yeah.
it's just to make sure there's a tear film in between, and because the lens is settling a little bit. Does that make any sense?
A lot of sense.
All right. So the other thing which is very interesting to look at is that if we look at the scleral over here, we can see that this direction is more red.
Mm-hmm.
The direction over here is more blue.
Yes.
So we expect a little bit of toricity in this eye as well. Well, the way we can calculate the toricity is if we look at the minimum and the maximum sagittal height over here. So it's saying the lowest point, which is this direction, is 4,730 microns.
Mm-hmm.
The highest point, which is probably going to be over here, is 490 microns. So the difference between that is 170 microns. So we're expecting that this is going to be a lens with toricity. And if we look at what it's suggesting, we can see it's suggesting an amount of toricity in the final order as well.
Clear.
All right. Do you've got any questions about this example?
Oh, I would like to try to change diameter if
Yeah.
can fit a different toricity. Thank you.
No problem. I think in this case, it's gonna order the same toricity, but in other cases it will change. It depends on the eye. You can also see that the volt is increasing.
Yes, I see. Great. Clear.
Yeah, all right. All right, so I'm moving on to the next example, if that's all right.
Yes.
So we got this guy over here. Is there anything abnormal you're seeing in this patient?
It's very pinguecola in nasal point. No, what is?
Awesome, good job. You're very, very smart. Over here we see this red elevation, and that is indeed a pinguecola. What kind of lens would you normally fit if you see a patient like this?
Oh, I need a notch. I need to create or larger diameter. It depends on it's a larger pinguecola.
All right, so yeah, you can create a notch or a microvolt.
Yeah, right.
Anything to bypass this. How many fittings does that normally take you?
Oh, it depends.
It depends.
Yeah, right.
All right, so for most people this takes about 2 or 3 tries, as far as I've heard.
Yes.
And there are 4 parameters you need to know if you want to order a notch or a microvolt, and that is the location, how high it is, how large it is, and at what axis it is located.
Yes.
So we're gonna look for that information. If I move my mouse over here, right in the center of this pinguecola. No, let me enlarge everything a little bit for you.
Okay.
I think it's about here. Oh. We can see that this pinguecola is 418 microns high.
High.
If I'm gonna order a Zen lens for this patient and order a microvolt, I want to distract about 50 microns to make sure the pinguecola seals really well. Otherwise, air bubbles are getting in. So in this case, I would order a height of 370 micron.
Okay.
Okay, so writing on the screen is a little bit difficult, but I'm gonna try. The other thing that I want to know is the location. So what is the distance of the center to the pinguecola? It is 8.5 millimeters. And I want to know at what axis it's located. That is 350 degrees. So I already have 3 of the 4 parameters that I need to know. The last thing that I need to know is this size, right? I need to know what width to order it. So in order to do that, I have to start moving my mouse a little bit. So I'm going all the way up top to this point where I think the pinguecola is starting. So I think that's right over here. And then I want to know the Y value. So that's minus 0.60. And I'm going to go all the way at the bottom, which I think is right about here, where the Y value is 3.11. So I want to know the difference between minus 0.60 and 3.11 millimeters.
Yes.
So that is going to be an order of 337 millimeters wide.
Okay.
So like we said, 380 microns high, I think, located at 350 degrees. And it was 8.5 millimeters away from the apex. Okay. So in that case, you have all the parameters that you need to order a microvolt for. And we're hoping to reduce that number of average refits for 3 to just order the right microvolt in just one shot.
Clear.
Do keep in mind that if you've got a pinguecola over here, if I'm going to click on the algorithms right now, it's going to say that, this is the maximum elevation, this axis over here.
Yes.
So the algorithm right now is not going to be very accurate, but it does help in estimating where the pinguecola is and how to order a microvolt. Do you've got any questions about this?
No. It's
All
very
right.
clear. You're very good.
Awesome.
Yes, very clear. So, wrong.
Yeah, I've got one more example. This is actually a normal eye. I'm just going to go into, because we've done 2 scleral lens examples right now, I'm going to talk a little bit more about soft lens fittings and hybrids, if that's okay.
Softness is better.
All right. So this is a normal eye.
Yes.
This patient had a refractive error of -7.50, so high myopic. Is currently wearing glasses, but he wasn't very happy with them. He really wanted to wear soft lenses, and he has fitted a couple of soft lens practitioners in the Netherlands, but he wasn't satisfied, he wasn't happy. So he ended up with me, and I have this beautiful device. But first off, I wanted to know why nobody else was able to fit him.
Yes.
So I was a little bit stubborn. Instead of using the ESP, I took a measurement with my normal topographer, and I calculated the sagittal height of my normal topographer. So because that is not measuring the full diameter of 1450 millimeters, it calculates the sagittal height based on extrapolation. And we know that the average sagittal height, I think, is somewhere around 3,400. And if your sagittal height is close to that, you can order a standard soft lens like Biofinity, Alcon, Cooper Vision.
Yes.
So that's what I did. I calculated the sagittal height. It was average. I ordered a normal soft lens for this man. He came back and I saw it floating over the eye everywhere. It was going up and down across the limbus, and I was like, okay, so probably this is the mistake all my other lens practitioners have made as well. So let's start from scratch. Let's make an image with the ESP. That is this image. And let's go looking for that sagittal height at 14 millimeter, because that's the average soft lens. So I typed in 14 millimeter, and I saw that the sagittal height was 3,530, which is a lot higher than I initially thought compared to the topographer I had. Okay. So based on the information that it is higher than average, I ordered a custom soft lens from Mark Enevy, which was the perfect fit. Of course, it's really difficult to think every time, what is the average sagittal height? Do I need to order a custom lens? So we made a little button for that in our software. It's called Artificial Soft Lens. If I click on that, it's going to do the suggestion right away. It's going to say high sagittal height, go custom. It can also say low sagittal height, go custom, or it can say normal sagittal height, go for a one-size-fits-all lens. So because of the high sagittal height and it said go custom, I went for a Mark Enevy lens. I don't know if you know those lenses.
Yes, I know them.
All right, custom soft lenses. So I clicked on our Saphir algorithm right here.
Yes.
And this is the final lens I ordered for him, and it was a perfect fit right away. So if I wasn't that stubborn as all my other lens practitioners in the beginning, and I did a standard topography first, or I did an ESP measurement first, I would have had the first fitting lens right away. So it's very easy to see if somebody needs a custom lens, if somebody just needs a regular lens, and that's just based on soft lenses, based on that algorithm. Does that make any sense?
Absolutely, yes. When I read eccentricity on the right of the, okay.
Yeah.
It's calculated, which arc?
It's calculated at 9 millimeters.
9.
Yeah, Arnoud, correct me if I'm wrong, but I think it's 9. That is because normal topographers, I think, measure it at 6 millimeters because they can't measure any wider. Because we can measure the full cornea, we measure the eccentricity a little bit larger.
That is correct, Ilse. Yeah.
All right.
Okay.
And if you want to fit a hybrid lens on this, it works the same. We've got the Ultra Health FC, and the Duet. You can click on the algorithm, and it's gonna make a suggestion based on sagittal height. And then we also have a fluorescein simulation available. And the fluorescein simulation, it works really well with RGB lenses. So then it's telling you what sagittal height, what fall to order.
Okay.
It's not going to make the soft skirt is always going to be medium. This is because Synergize, the American USA manufacturer, they're not able to give us any information about the soft lens so far. So right now we can only make a suggestion on the RGB part. The reason for that, I don't know, but that's why we only tell you the center.
Okay, clear.
All right, so that's me about the software. If you've got any questions or any technical questions, you can find me at any time.
Thank you so much.
All right.